Hello, welcome back to ECE484. This is lecture number 8, fall 2021. Okay, so let's remind ourselves what we did yesterday. Okay, so I'll repeat again. We talked about tracking, actually 2 lectures in a row, I think now. And in summary, we saw that you get set point control. In other words, you track constant references if you have stability, and if the product of the controller and the plant has a pull at s equals 0. And that's what you know as integral control for step tracking. And then the generalization of this is the internal model principle, which says that y, the output, will track r if the controller and the plant include the same bad poles as the reference's Laplace transform, r of s. Okay? And I invite you to think about what that means for the disturbance, right? So you can try and think about how the disturbance comes into the picture. So for example, if you have constant reference, you know that you want an integrator pulled at the origin, what happens if the disturbance is also constant? Will you track? So you can think about that. Okay, we started chapter 3, which is sort of a control design method, kind of building up on our kind of library of control design methods that we have. And we talked about pole placement. And the idea here is simply to design the controller to assign, in other words, to place the roots of the characteristic polynomial for the closed loop system. In other words, we're calling those the closed loop poles. We know that the poles of any transfer function associated with this loop have a subset of the roots of this characteristic polynomial. You know, usually they'll be the same set, but in general it'll be a subset. Okay, so to do this, we first, assuming that we can actually design such a controller, the first thing we have to do is we figure out where do we actually want to put the poles, or the roots of pi. Now, clearly we want stability, so we want them all to have negative real part, but beyond that, we want a little bit more in terms of performance. And so what we did yesterday is that we converted transient specs into good regions of the complex plane. Okay? And we talked about settling time and overshoot, and if you have those kind of specs, you end up with a good region which looks something like this, right? So a cone with its top chopped off. Okay, so now that we kind of have a way of picking, desirable pole locations, it's time to actually come up with the controllers. Okay, so at the end of last class, I stated the problem, the pole placement problem, and so now we'll just state the solution, and then we'll start doing some examples. Okay, so here we go. And so the result here is theorem 321 in the notes. And it's basically somewhat intuitive, right? Let me just go back up here for a second. If you look at the characteristic polynomial, it seems clear here that if I choose DC, so the denominator of the controller, and I choose the numerator of the controller sort of wisely, I should be able to make that polynomial almost anything I want. Right? I can kind of erase the structure of the plant in some ways. And indeed, that's what the result says. It says if your controller has enough kind of gains for you to play around with and tweak, you can assign the roots of this polynomial. And so that's what the theorem says. So a technicality, we have to suppose that NP and DP are coprime. Right? So that means that the numerator of the plant and the denominator of the plant do not have any common roots. Okay? Because I mean, if you go back up to the expression for pi of s, if the numerator and the denominator have common roots, you can factor them out, right? Because they show up on both sides of the plus sign, and those roots are fixed. I can't change those. So it's like a technicality. And of course, in practice, this will always be true, right? You'll always reduce your transfer function. Okay, then there exists an mth order controller to solve the pole placement problem if and only if the controller has sufficiently high order. And for us, that means at least one below the order of the plant. So n is the order of the plant, m is the order of the controller, and this says that if your controller has order at least n minus 1, so order of the plant minus 1, you can place the poles. Okay, so the intuition being the controller has sufficiently many gains for you to play around with. A few comments. If C of S has order exactly n minus 1, then there's a unique controller. In other words, let me write that down. Then the controller is unique. Okay? So what that means essentially that the desire to place the poles completely specifies the controller, and there's no other room to do anything else besides place the poles. If C of S has order greater than n minus 1, then it's not unique. Then the controller is not unique. And we're going to use that actually later on in this chapter. We're going to use that fact, right? Because what that means is that if you have a high order controller, you can place the poles, plus you can also do other specifications. Yeah, n is the order of the plant. So if we wrote this down last time, we have an nth order plant, an mth order controller. That's right. Yeah, so n is the order of the plant. So we're going to use this non-uniqueness in the controller to place the poles plus meet additional specifications. Okay, so you'll see later on that we will bump up the order of the controller. Finally, if C has order less than n minus 1, then the pole placement problem isn't solvable in general. I say in general because you might get lucky, right? If you pick a certain set of poles, you might be able to use a lower order controller to get those poles. But when I say in general, I mean arbitrary. Arbitrary selection of desired pole locations, you need order at least n minus 1. Okay, let's do a simple example to sort of get our feet wet and to see what's going on here. So this is the type of problem that certainly you would have been able to solve after your first control course, but let's put it in the context of this pole placement problem. So our plant is first order, and it has a pole at s equal to 1. So if we were to draw its pole, we've got a pole here at 1. Okay? And so for this guy, n is equal to 1. Now, if we wanted to solve the pole placement problem, what we're saying is we need at least order n minus 1. So we're going to take a n minus 1 equals 0, in this case, order controller. So what is a 0 order controller? It's just a gain, like a proportional controller. So in our notation from last class, we just have a g. So remember, the g's were the coefficients in the numerator of the controller. The f's were the coefficients in the denominator. Okay, so in this case, it just becomes a gain. Okay, so the question is, can we place the pole of the closed loop system of the characteristic polynomial arbitrarily with this controller? And the answer, of course, is clearly yes. So let's look. So then we get that the characteristic polynomial is the product of the denominators, so s minus 1, plus the product of the numerators, plus G0. Okay? So, and clearly, we can place the root of pi anywhere on the real line. Okay, so I guess I think I mentioned this yesterday, but let me just remind you that when we're talking about desired pole locations, we want to be able to implement these controllers on real hardware. So we will always want symmetry about the real axis, right? So if you have a complex conjugate, if you have a complex pole in your desired pole locations, you need to have its conjugate there. Otherwise, your controller is going to end up having complex gains, which you can't implement, right? You won't be able to implement those. So, so that's why our desired pole locations are always symmetric about the real axis. And so in this case, the only option is to pick a pole on the real axis, on the real line. Anyway, so in this case, say that our desired pole location is lambda, right? So lambda was the notation we used for kind of the desired poles last class. Then, of course, we get a design equation. G0 equals 1 minus lambda. Okay? And so in the picture over here, maybe our lambda was this guy over here. And then we want to pick G to get that value of the pole. Okay? And of course, in this case, it's such a simple example, such an easy example that you would have been able to do this before, and you would have possibly drawn a root locus, and you know that you can basically, by picking different positive values of G0, you can pick anything along this line for that pole. Okay? So a simple first order example. All right. So instead of doing the general design equations, let's derive them for the case of a second order plant. And you can look at the notes if you want to see the general expression. So let's say that instead of the general case, and for that you can see the notes, let's generate design equations for a second order plant. Okay, so our plant, using the same notation we've used last class, is a numerator over denominator. And so remember, we used b's in the numerator. And a's in the denominator. Okay, so the theorem above says that if our plant is second order, the controller has to be at least order n minus 1. So I'm going to pick a controller of order n minus 1 to get the unique case. Okay, so I'm going to take my controller, to be first order in this case. So G1s plus G0 over F1s plus F0. Now, remember last time I said that, in the case that there's a bit of asymmetry here in these expressions, right? So like here, without loss of generality, I've divided the numerator of the plant and the denominator of the plant by the leading coefficient here, so that I get a 1, right? I can always do that. But I have not done that in the case of the controller. I kept F1 there. And the reason for doing that is simply to, I think I mentioned this last time, is so that we get kind of a nice structure in our design equation. Okay, sorry. Okay, so let's derive the equations. And I mean, just to give you an idea of how it works. Okay, so the characteristic polynomial in this case is, of course, I've written this down a few times, but let's write it again. Again, why do I care about that polynomial? That's the polynomial which, first of all, determines stability of the closed loop system, and the roots of that polynomial essentially show up in all the various transfer functions associated, show up as poles in the various transfer functions associated with the loop. Okay, so doing some uninteresting algebra, just multiplying out all those polynomials and then collecting terms, you get this following complicated expression. So let me write it down and then we'll continue. So you see you'll get a cubic polynomial because the plant has a second order denominator, and then I multiply that by the first order denominator of the controller, and so you're going to get a cubic. And so if you collect all the terms, you get stuff like this. Plus, by the way, as I'm writing this down, keep in mind that it's the F's and the G's in the controller. Those are the things that we get to choose. The A's and the B's are fixed by the model of the thing you're trying to control. So it's the F's and the G's that are the unknowns in some sense. All right, so we do it again for S squared. And again, there's nothing interesting really going on here. You can verify that I did this correctly. Plus A0, F0, plus B0, G0. Okay, so we get this complicated expression. Okay, fine. We need to solve a pole placement problem, so we need sort of a desired characteristic polynomial. So I'm going to write that below. So I'll say that the desired characteristic polynomial, I'm going to write it as pi with a subscript des for desired. And here's where you have to make a choice, right? Here you have to pick 3 in this case, because the plant is second order, the controller is first order. 3 desired roots. So the lambda I will be in the good region of the complex plane, which we talked about last class, right? So first you'll figure out what the good region of the plane is, and then you pick these poles. And so, you know, we'll talk a little bit more about this as we go, but the typical picture you might have might be something like this. So here's our good region as I drew before. And remember, we generated that good region assuming the characteristic polynomial was second order. In this case, it's third order. So what we'll want to do is we want to pick 2 of them to be dominant. Let's call that lambda 1, lambda 2, and then the third one to be non-dominant, right? So the idea is from chapter 2. So maybe something like that. Okay, so you pick your desired pole locations. Okay, and now you have to expand this out because we want to compare coefficients between the polynomial. Okay, so I'm just going to write this as alphas, right? So you get some coefficients alpha. Right? You change the lambdas, you get different alphas. I'll mention here that you can use the MATLAB command to do this. Convolution, right? So it'll convolve to do that calculation, right? So once you pick your desired pole locations, you can generate this polynomial. All right, so now we're just going to equate coefficients. So in other words, we'll look at the s cubed terms, compare them, make sure that the coefficient is the same. Look at the s squared terms, compare the coefficients, set them equal. Okay? If you do that, you get this nice equation. So we get the following equation. Let me write it down and then we'll talk about it. Okay, so it's a linear equation, so I've written it as a linear equation. Again, the unknowns are the controller gains. So let's write the controller gains here, F1, F0, G1, G0, and these are controller gains. Okay, the thing that we want to solve for. So converting lambda from alpha is just algebra, right? I mean, yeah, you could, that's right. You're correct. I'm just doing multiplying out this polynomial. It's just algebra. You could probably write down a formula. I mean, certainly you could write down a formula for alpha in terms of the lambdas. Problem is, it might be of limited use because then you might end up with a fifth order closed loop characteristic polynomial. And then you're going to have formulas for the fifth order polynomial, right? So it's, you know, in the old days, you'd have to write it out and multiply it out in an exam or something. In these days, in this term anyway, I suppose you could use MATLAB to do that calculation. And certainly for the lab, you're going to want a script, right? You're going to want a script to automate this. We'll talk about design, but like, it's quite possible that you pick your first choice of desired pole locations and things don't work out exactly as you want. And so then you want to change the desired pole locations and iterate your design. And so you're going to need these alphas again. So you kind of want to be able to do that. You'd like to automate that if possible. Okay, those are the controller gains. The right-hand side of the equation depends on the desired pole location. So I'm going to put the coefficients of this polynomial will show up here. Okay, so indeed, 1, alpha 2, alpha 1, alpha 0, and this, of course, depends on desired pole locations. Okay, and then what's left is the 4x4 matrix on the left. Okay, and that has a nice structure, and it's going to come from the plant. So let me partition this into the first two columns and the second two columns. So I'm going to put a partition line here. Actually, let's use a different color. Okay, so the first two rows come from the denominator of the plant. So remember, there's our, let me see if I can get them both on the screen. There's our plant up there. So look at the coefficients of the denominator polynomial for the plant, right? It's 1, then A1, and then A0. I'm just going to list those coefficients starting from 1 at the top in the first column, and then pad everything with zeros. So 1, A1, A0. Okay, I'm missing one term, so I'm going to pad with 0. For the second column, I'm just going to shift everything down, and then again, pad with zeros. So I'm going to shift down. And we get this. Okay? That's it. Those are my first two columns coming from the denominator of the plant. Okay? Let's go back and look at the numerator of the plant. So the numerator, the coefficients of the numerator are B2, B1, B0. Okay? So I'm just going to list those coefficients in the same way for the next column, and again do that shifting. So we have B2, B1, B0, pad with 0, and then shift. All right, and so this part here, first of all, I'll say it has a very nice structure. And it depends on the plant model. right? In particular, the polynomials, the numerator and the denominator. Okay, so you solve the equation, you get the controller gains, you now have your controller. Let me make a few comments about this controller, or this equation, and also this approach to control design. First of all, the square matrix that we get up there is an example of a Sylvester matrix. So that's kind of a trivia more than anything else. So the square matrix above is an example of a Sylvester matrix. Okay, that's just, again, that's just sort of a factoid, if you will. And I mentioned, if you're more interested in that, you can see Appendix 3A. If you're kind of interested with, where that matrix, how it's related to polynomials and so on. Okay, so the next comment is important from a design point of view. So we obtained, or we found, the good region. Oh, when you get a chance, can you go over to high level? Oh, okay. Yes. So what's happening here is that we have a plant that we want to control in closed loop. And the approach that we're taking here in this chapter is to turn our design specs into desired regions in the S-plane, so desired pole locations. Okay? We know that for a second order plant, we need at least a first order controller to be able to solve this problem. That's that theorem that I wrote earlier. Okay? So what I want to do in this section, what I'm trying to do is come up with equations, design equations, to actually generate the controller which will place the closed loop poles at the desired locations. Okay? So we started with a second order plant, first order controller. If we hook those two things up in unity feedback, we will get the following characteristic polynomial, this complicated thing. Okay? We then said, okay, but we have a desired characteristic polynomial. We multiplied that all out, and we got the desired characteristic polynomial. So we want the actual closed loop characteristic polynomial to be equal to this desired characteristic polynomial. Okay? So then we just compared coefficients. So coefficient on s cubed, that has to equal 1. The coefficient on s squared, that has to equal alpha 2. Coefficient on s has to equal alpha 1, and so on. And when we do that, you get this equation. Right? And so again, if I solve that equation, plug those gains into my controller, the resulting closed loop system will have characteristic polynomial equal to the desired characteristic polynomial. And so hopefully we'll meet the specs. And that's what I'm talking about now. So we found the good region by assuming pi of s, characteristic polynomial, is second order. The real pi of s is usually much higher order. Right? And we just saw that, right? If you start with a second order plant, we ended up with a third order characteristic polynomial. So we need to justify. Remember we said that we need to justify this assumption. So to justify our assumption, in other words, the assumption that pi is second order, we should pick our desired pole locations so that there are two dominant complex conjugate poles. Okay. Because again, the good region was generated assuming a second order model. In fact, a second order underdamped, right? And so we want these two, we want the dominant poles to be complex conjugates so that it's approximately an underdamped second order system. Okay, and that's sort of what I drew up here. That's kind of the idea behind that picture, right? You have two dominant complex conjugate poles, and the third one is further to the left. Okay, the last comment is about the practicality of this approach. It almost seems too good to be true, right? We can just take any plant, put it in feedback with a high enough order controller, and we can sort of place the poles anywhere we want. I mean, and so there are some limitations, of course, right? It's not as great as it seems. There are certain trade-offs. Okay, so the first comment would be that, which I won't write down, is that suppose I'm trying to control like a steamship, a huge boat, right? If I put it in closed loop system and I place those poles really far to the left, I mean, in theory, I can do it. But in practice, if I want to actually move this ship quickly and get a really fast settling time, it's not going to be possible, right? I'm going to need a huge amount of energy to move this ship and then get it to settle down at a particular location, right? So what you're going to encounter, and you'll see this in the lab, is that if you place your poles too far to the left, like you're asking the system to respond faster than it would naturally want to do, and you're going to try to do this through feedback. And the only way to accomplish that will be to use high amounts of control effort, okay? And there you're going to run into the limitations of the motor. So the one thing is that, in theory, we can place our poles anywhere, but in practice, because actuators have limits, you won't get the response that you theoretically expect. So that's one issue. The second issue is what I'll write here, is that we have no idea where the closed loop zeros go. Will end up. Okay. And that means essentially that you don't know what's happening exactly in the frequency domain, right? Because we know that Bodie plots depend on poles and zeros. And so this is a significant practical limitation. Okay, so what may happen here is that our design, what does that mean in terms of things you might actually, observe? So our design may end up with poor stability margins. So that's robustness to model uncertainty. Right? So you might, what you would have called in third year, gain margin, phase margin. So those characterize in some sense how much tolerance your system or your closed loop system has to model uncertainty. So the solution to that is that after you design your pole placement controller, you should always take a minute to look at the margins that you're going to get for that controller. And that means looking at the Bodie plot of the loop gain or the Nyquist plot of the loop gain. Okay. So after designing CFS, we should always check the Bodie plot of the loop gain, which in this case is going to be the controller times the plant, to get a handle on what is happening in the frequency domain. And I'll mention an example where I do that. So 324. Okay, so I guess the moral of that last point is that you have a lot of tools in your toolbox at this point. Use them all. Use what you know. Design your controller doing pole placement. That's a very reasonable thing to do. But then check, right? Check the stability margins, the bandwidth, and so on. These are all things you might want to look at. Okay, let's do an example where we use this pole placement design procedure. Okay, so the plant looks like the lab, like a DC motor. So there's our plant model. Specs, closed loop stability. Okay, I'll write that for now. At some point I'll stop writing that as a specification because of course it goes without saying. Okay, it's the fundamental specification. And our settling time, less than 2 seconds. Okay, so let's go through the motions here, the steps. So first, characterize the good region. Right, and when we do this, we assume that pi is second order. So for now, assume pi of s is second order. Okay, now the only transient specification that we have here is the settling time. And so our good region in this case is going to look like so. There's our good region, and this distance is 4 over the maximum desired, or maximum allowable overshoot. So in this case, 4 over TS max, which in this case equals 2. Okay, that's the spec above. Okay. Step 2. Pick desired pole locations. Oops. Pick desired pole locations. Oops, I think I've got a problem here. Sorry, let me fix a technical issue. All right, sorry about that. Pick your desired pole locations. So in this case, the plant has 2, n is equal to 2. M is equal to 1, order of the controller. So we need 3 desired pole locations. Okay, so as I mentioned in that remark, I'm going to pick 2 dominant ones. So pick 2 dominant poles. In the good region. In this case, I'll pick lambda 1 and 2 equal to -3 plus or minus j, and then a non-dominant pole. And a third non-dominant pole. So lambda 3 in this case, I'm going to take to be -15, right? I mean, our rule of thumb was 5, so I'm just using that. Of course, in practice, again, if you have actuator limitations, it might not be possible, right? You might hit the limitations of your actuators. Okay, so with that, we get our desired characteristic polynomial. Oh, shoot, I made a mistake here. I apologize, I skipped a step. Step 2, so give me a second, let me give myself a bit of space. Step 2 should be determine the controller structure. We're going to see a few different structures, so. Okay, so again, n equals 2. So m equal to n minus 1 equals 1 to guarantee that the problem is solvable. Okay, so our controller in this case we did the second order derivation, so it's going to look like this. All right, so characterize the good region, determine your controller structure, pick your desired locations, and so now this makes sense, right? Our plant is second order, the controller is first order, so we need 3 desired pole locations. Pick 2 of them to be dominant, the third to be non-dominant, and now we have a desired characteristic polynomial. So there's the dominant ones, and then the non-dominant one. Multiply it all out. In this case, we will get what we called alpha before. Okay, and so now we have everything we need. We have the information of the plant. That's going to give us that Sylvester matrix. We have now our desired characteristic polynomial. That'll give us the right-hand side of our linear equation, and then we just solve for the controller gains. So step 4. Set up and solve design equations. Right? So remember the plant multiplying out the denominator. Where did those lambda values come from again? I picked them. Right, step 3, that's the design choice. First I characterized the good region, then I picked them. You pick different ones if you don't like those, right? The guidance that I suggested is you want 2 dominant ones, which are complex conjugate, and then 1 which is non-dominant. If you don't like those numbers, pick different numbers. But what we want is, again, 2 dominant poles in this region, 1 non-dominant. If you don't like those numbers, pick a different number. All right, so here we get compare it to our general form. The B2, B1 coefficients are 0, B0 equals 1, A1 equals 1, and A0 equals 0. All right. So that's it. That's all the information we need to write down our equation. So let's do it. Okay. So the first column just comes from the denominator. So we have 1, A1, A0, pad with zeros. Shift down. 1, that's this one here. A1, A0. Third column comes from the numerator. So in this case, B2 and B1 are 0, and then B0 is 1. So we get 0, 0, 1, pad with zeros, shift. Controller gains. And then the right-hand side comes from the desired characteristic polynomial, which in this case is 121, 100, 150. Solving. Gives us 1, 20, 80, 150. Okay. So at this point, as I said in that remark, your closed loop system will have the poles that you want, but you still want to simulate it, check the Bode plots, do all that stuff. So step 5, simulate / test closed loop system with the controller that we just generated which is this guy here, right? The gains we just computed. By the way, it's maybe of interest to note that if you draw the poles and zeros of this controller, you will see that we have a 0 around here, pole over here, so this is -20, -1.8, so this is pole 0 map of the controller. And you might recognize this, right? This is a lead controller. This is what in third year course you would have called a lead controller, or you can think of it as a PD controller. Essentially, this pole placement has generated for us a PD controller. So I'll just mention that. We've designed a lead controller. In other words, a PD controller. With the same kind of practical derivative term that we talked about last class. All right? So that's the basic idea. Those are the steps. Let's see. Characterize the good region, figure out what kind of controller you want to use, pick the desired pole locations, generate the design equations, and finally, test the controller. Okay. I got 2 minutes. I'm just motivate the next section. So in this example, we didn't actually do. No, I didn't simulate it. You can simulate it. Sorry, that's right. I didn't simulate it. In the notes, I guess I'll mention that there's a MATLAB script in the notes, which unfortunately one of the commands that I used in that MATLAB script to do pole placement doesn't exist anymore. So I mean, it's very simple to change and update. So if you wanted to automate such a design procedure, that script could be useful. Okay. So one thing about this controller that we just designed is that it was only proper. It wasn't strictly proper. In other words, the degree of the numerator and the degree of the denominator were equal. And sometimes in practical applications, you don't want that. So strictly proper controllers are often preferred when the reference and therefore the tracking error is discontinuous. Example, sequence of steps. Okay. And I'll draw a picture of that next class. But basically the idea here is that if your reference is like a square wave, jumping up and down, so discontinuous, that means the error is going to have this discontinuity in it. And what that's going to mean for your controller, if it's just proper and not strictly proper, is that there's going to be a discontinuity in the control signal. In other words, the command that you're sending to the plant. And sometimes for actuators, you don't want that. Right? You don't want your motor kind of quickly changing directions because of the discontinuity. And so in that case, what we'll see is that you might want to use a strictly proper controller to save the actuator, right? Avoid this banging. If you're controlling a water system, you don't want valves, closing and opening really quickly. Maybe you want more gentle smoothness. And so what we'll do is we'll refine, or we'll next class or next week, we'll give another design procedure for pole placement where we get these strictly proper controllers. Okay, so we'll stop there. I will post problem set 3 tomorrow, and also the solution for problem set 2, as well as the tutorial video, and we'll continue next week. So have a good weekend. Oh, how can we, okay, so the question is, how did we get the square matrix on the left here? So, which part? No, yeah, okay, so again, the matrix here, I'll come back to this in a second. The matrix only depends on the plant model. Does not depend on the desired poles. So the square matrix comes only from the plant. You give me the plant, I know exactly what to put in that matrix. It's the right-hand side that depends on the desired poles. Okay, let's go back. So notice you see here, it's just I'm just plucking coefficients off of the plant model. So let's go back. Here was our plant. And so I look at the coefficients. In the numerator, the squared term is 0. The s to the power of 1 term is 0. And the s to the power of 0 term is 1. So that's my numerator. That gives me my b's. The denominator, the coefficient on s to the power of 1 is 1. And the coefficient on s to the power of 0 is 0. Okay, so I've now got my a's and the b's. And now I fill them in. So the coefficients of the denominator are 1, a1, and a0. So 1, a1, a0, pad with zeros. Second column is I take that first column and I just shift everything down by 1. So this is the padding of a 0. Now, first coefficient, second coefficient, third coefficient. Now, this kind of indicates that now we switch over to the numerator. And so now I use the b's. So b2, b1, b0, pad with zeros. Shift down, so shift everything down 1. So this is my padded 0. And I've got b2, b1, b0. So that's the matrix. It depends only on the plant. And then this here came from the desired characteristic polynomial. So I've just listed the coefficients of that polynomial in that vector. Okay, so again, if there are more questions, I probably have a couple of minutes more. Otherwise, I will see you next week.